All right, so the first thing that we are going to talk about today is to wrap up our review of the important electrical and mechanical things that we need to understand in order to have a good idea of how these MEMS devices are going to behave. So this last couple of pieces of information that I want to give to you guys on this review material are how to determine the resistance of a section of silicon. Particularly, we're going to be dealing with doped silicon for this. There are going to be certain structures that we are going to literally talk about integrating resistances into those structures so that when the structure experiences some deflection, the resistor itself will experience a change in its geometry, and that change in geometry leads to a change in resistance because of the piezo-resistive effect, and that is going to be one of our sensing tools. Okay, so resistance as a function of geometry can be defined as length divided by electrical conductivity multiplied by cross-sectional area A. So if we have a rectangular beam or a rectangular section of material like so, where we are going to make the assumption that the current that's passing through is in this direction. Our cross-sectional area A is here. So let's define this dimension as our length. This dimension as our width. And this dimension as our thickness. And so we can slightly modify our resistance expression to be L over sigma E times the width multiplied by the thickness. Okay. So what is interesting about the resistors that we are going to be dealing with is that they will typically be of some fixed thickness. And so what I mean by that is we are going to form resistors by either performing a diffusion doping process or an ion implantation process, and we are going to define our resistors in one fabrication pass. So the implantation depth or the depth of diffusion will define the resistance that we get. Everything will be of a particular uniform thickness. So instead of dealing with absolute resistances, we largely deal with what are called sheet resistances in MEMS devices. So for a sheet resistance, the absolute resistance R is R square, the resistance per unit square, multiplied by the length dimension divided by the width dimension, which implies here that R square is equal to 1 over the electrical conductivity multiplied by the height. So, for example, let's say that we had a length here where L is equal to, let's see, 10, I would say 20, 40, 60, 90 microns. And a width dimension that is, let's call it 20 microns. Sorry, let me write that a little bit better. our absolute resistance of this guy would be 4.5 times whatever the sheet resistance of each individual square is. So that could be somewhere between 100 ohms per square to all the way up to 1,000 ohms per square or more, depending on what kind of doping we put in, whether it's single crystalline silicon or polysilicon. All of those types of things will have some level of influence on our sheet resistance, okay? Now, I mentioned a little bit ago that we are going to implement resistances like this in piezo-resistive sensing things. We're not really ready to go full into detail on that, but I do want to point out some of the structures that we might see. So we might see something that looks like this. So this would be considered a serpentine resistor, okay? Because it turns back on itself and it looks snake-like, all right? So let's break this up into some number of squares. So I'm going to put a blue dot in our normal squares and a red dot in our corner squares. So if I counted correctly, there are 33 normal and there are 6 corner squares. Why I'm making a distinction here is because the way that our current density is going to work out, our corner squares aren't going to have the same sheet resistance as our regular squares will, okay? So the sheet resistance of a corner will be roughly 3/5 or 60% of the sheet resistance of a regular square, okay? So we're going to have to take into account that change in the current distribution as it flows along that serpentine path by differentiating between our normal squares and corner squares. Now, you might be asking yourself, well, why would we ever use a serpentine pattern like this, okay? So for my integrated circuits students that had me last quarter, we talked about using serpentine resistances in order to reduce the lateral length of a resistor, right? We're taking up more area, but we're not having to do extremely long runs of a particular material in order to achieve a resistance. In a MEMS device, there's an even better reason, okay? So that piezo-resistive effect that I've referred to a couple of times at this point is typically pretty small. So if we had, I'm going to try to do this in a slightly different color here. So if everything to the left of this blue vertical line was connected to our anchor points for a beam, and everything to the right of the line was in the beam that is allowed to deflect, having a long serpentine resistor like this will allow us to effectively amplify the change in resistance, because more portions of the resistor are going to undergo that stretching as our beam deflects. So we'll see a larger relative change in the resistance, which is easier for us to measure. Okay, so that's why we would run a serpentine series of squares like this in a MEMS device. It makes that relative change in resistance, which is turned into an electrical signal by the piezo-resistive effect, into a larger and more easily observable signal. Okay, does that sound reasonable? All right. So it's because when the current goes around. All right, so let me draw something else here real quick, okay? So if we have a DC current flowing through a wire, we would normally expect that the current distribution is uniform along that section of wire, okay? Well, when we bend it, what we're going to see is we have a uniform current density, and then it gets concentrated here, and it doesn't reach that outside corner. And so the area that the current sees as it flows around that corner is about 60% of the actual area of the square. And so that's why the resistance is changed. That's it. It's just purely a function of what our current density, or the amount of material that our current density sees as it travels along that oddly shaped geometry. So. All right. Let me turn off this fan because I can't hear you. Sorry. So,
like, if we are not looking on the electrical part, we go to the fluid.
Right.
Will that affect this?
I don't think so. And so I say I don't think so. That is a way for me to say I don't know for sure, but I'm not entirely sure. And the reason why I'm not entirely sure is because for a fluid flow, you have to take into account things like capillary action, surface tensions, and all of that kind of good stuff. And if I'm being entirely honest, my background in that isn't as good as a mechanical engineer would be, because I'm an electrical engineer. So I would assume, being a relative, I would say I'm above a layperson, but I'm definitely not an expert in that when, capillary action and things like that are pulling the fluids into your microchannel, it should spread out pretty evenly over the entirety of the surface. But I don't know for sure because I have not done fluid dynamics. So you very likely know more than I do about that particular case. So. All right, let's briefly talk about crystal planes and all of that kind of good stuff, and then we'll get into our next section. All right, so this is going to be an extraordinarily brief thing here. Just as a heads up, because I see somebody taking pictures of notes because they came in a little bit late. My goal this weekend is to get all of these videos uploaded and also get you guys at least one homework assignment uploaded so that we can kind of catch up and all that kind of good jazz. So I I would expect to see all of my lecture videos uploaded by 5 p.m. on Saturday. That's my goal, is to get everything up for you guys. So, all right. So let's look at a simple cubic structure where this is going to be, each of these dots represent one of our lattice points. And I'm just going to play connect the dots really quickly here. So this simple cubic structure contains multiple families of planes, okay? For silicon, we're really going to concern ourselves with 3 specific families of planes, okay? So the first one that we're going to deal with that was not my intention. Stop erasing. Okay, I'm using a thicker thing because this dumb computer is just going to keep erasing that and it's going to drive me insane. So this first one here is representative of the 1, 0, 0 family of planes. So any of our faces of our cube would be represented by this particular family of planes. In silicon in particular, this plane has an areal density, so the number of silicon atoms per cubic centimeter, of about 6.8 times 10 to the 14 silicon atoms per cubic centimeter, okay? That number can be determined mathematically if we were to look at the plane. So if we consider this to be an area representative of our 1, 0, 0 plane, where this height is A, this width is A, the interatomic spacing for silicon, where A will be equal to 5.043, I believe. No, 5.43 angstroms. What we would see would be a silicon atom on each corner and a silicon atom in the center of the face. If we treated these as hard spheres where the edges of the spheres are going to be touching each other, and we perform the simple math here, we would have what looks to me to be 2 silicon atoms per our area A squared, which should give us this number as our areal density, the number of silicon atoms per unit area, right? So that's what the 1, 0, 0 family of planes looks like. Our 1, 1, 0 family of planes are going to be these guys. So the 1, 1, 0 family of planes has a different area. The height is still going to be exactly A, but using good old Pythagorean theorem, we can see that the distance along this bottom edge across the diagonal of our unit cell is going to be the square root of 2 times A. And because of the crystal lattice structure of silicon, what we're going to see is we have an atom on each of the corners. We have an atom in the middle of each of our diagonal paths. And then there's going to be a whole silicon atom up here as well, because we have that zinc blend or diamond crystal lattice structure that is 2 face-centered cubics interposed with each other. So we have, let's see, So a quarter plus a quarter plus a quarter plus a quarter, plus a half plus two more. So that looks like 4 total atoms divided by this larger area gives us a surface density of 9.6 times 10 to the 14 silicon atoms per square centimeter. Excuse me, I keep wanting to do per cubic centimeter because I'm used to doing concentrations. And then our last family of planes, let's do these in green, will be the 111 family. Like so. Where this 111 family of planes looks like this, where this length is the square root of 2a. And these are equilateral triangle. I wanted to say isosceles, but that would be incorrect. So the length of all of the legs is exactly equal to the square root of 2a. And we would have a silicon atom on each vertex of this triangle, as well as a silicon atom at the halfway point of each of those legs of the triangle. So there would be 2 total silicon atoms, but our area here is going to be whatever the trig tells us to. I can't think right now, so don't worry about that. You guys can figure it out if you're that particularly interested in it. It's a right triangle, the area of an equilateral triangle, whatever that is. And we're going to get 7.83 or 7.8 times 10 to the 14 per cubic centimeter. Okay. So because each of these planes has different densities of atoms, they are all going to have different mechanical properties, which means they're all going to etch differently, and certain planes will be better used for certain types of structures, right? And then that circles us back around to all of the mechanical things that we talked about at the beginning of this review session, which we started at the beginning of this week. So we are done with our review of all of the mechanical and electrical concepts that we're going to need to be successful in this class. Now let's talk about something I think is more interesting, and that is the concept of noise. Okay. So let's talk about what noise is. We are experiencing lots of it right now. Some of it earlier because of the fan, a little bit of it because of the construction going on across the street. There's noise generated when we shift in our chairs and things like that. Noise is really just any kind of unwanted signal that we don't particularly want to be dealing with, right? So in the electrical domain, noise is attributed to the random motion of electrons in a conducting material. And in the mechanical domain, noise is attributed to the random thermal vibrations of atoms in a mass. And these quantities are largely coupled because they kind of represent the same thing, right? Our electrons are tied to an atom and our atom is moving. We have both mechanical noise and electrical noise. It just depends on what kind of interface that we're looking at, right? So from these two definitions, the most important takeaway is that noise is a random process, meaning that the value of noise cannot be predicted at any time, even if past values are known. So what I mean by that is let's consider two simple functions, right? So over here, let's say that we have F1 as a function of time. And let's make F1 be a simple periodic function like a sinusoid. You good? So this function can be characterized by its periodicity, right? The function is periodic, meaning that it repeats itself at regular intervals. And from this, we are able to accurately predict a value of f1 of t when our time, lowercase t, is some value larger than our period, because we know the past values. If we look at a different signal, and really it can be any aperiodic signal, call this F2. So let's give us some garbage like this. Right. In this case, the function has no period or discernible pattern. So instantaneous values of F2 of t cannot be predicted from past values of the signal. All right, so if noise is a random process, how do we analyze it? Okay, so while the instantaneous amplitude of a noise cannot be predicted, it is often the case that the average power of the noise can be predicted. By observing the noise for a very long time, we can develop a statistical model for some particular noise sources. So this largely has to do with the fact that the overwhelming majority of noise sources obey a simple Gaussian distribution. Not all of them by any stretch of the imagination, but most of them do. So let's look at the noise voltage for a resistive load. So what would the average power delivered to a resistor by a periodic function look like, right? So the average value of a function is the integral of a function over one period. So I'm going to define my boundaries of integration from negative t over 2 to positive t over 2. I'm going to integrate the instantaneous power. So if our function f1 was a voltage, our instantaneous power absorbed by a resistor would be f1 of t quantity squared divided by the value of our load resistor with respect to time. And we take the average value by performing this integral over one period and then dividing by the duration of the period, right? This is how we compute the average value of any periodic function. We integrate the function over one period and then we divide by the length of the period, giving us the average value. If we have a aperiodic signal, we have to carry out this measurement over a longer time. So for our function f2 of t, we're going to do something similar here. We're going to have 1 over t multiplied by the integral from negative t over 2 to positive t over 2 of our signal f2 of t squared divided by our load resistance, just the instantaneous power generated by this time varying voltage waveform dt. But now we are going to take the limit of this as t goes to infinity. Okay. So this is what our average power is going to look like. We are going to define our noise voltage as Vn squared is simply our average power divided by our load resistance, which comes out to be the limit as t approaches infinity of the integral. Looks like I'm missing a term here in my notes, so I'll need to double check this, but I don't know how what I'm about to write down couldn't be correct. Sorry, I no longer should have the over RL because I took that out. F2 squared dt. All right. Okay, so one thing that I want to point out here is that our noise voltage is measured in volts squared here, okay? It is related to the power. We have just simply thrown away the value of our arbitrary load resistance or divided effectively both sides of our equation by our arbitrary load resistance here, okay? So as I mentioned previously, for most physical noise sources, the instantaneous noise amplitude follows a Gaussian distribution. That means roughly 68% of all noise amplitudes will fall within one standard deviation. So I'm going to attempt to draw a crappy Gaussian distribution here. So let me draw a set of axes. We have our standard bell curve like shape, or an attempt at one at the very least. Something like this. We call this one standard deviation, and I'm going to put one STD on both sides of here, because if I'm not mistaken, standard deviation is also usually sigma, which we know is conductivity, but also strain. We're going to just call it a standard deviation. So 68% of our noise is going to fall within that range. When we were 3 standard deviations out, so somewhere way over here, on either side, only 0.3% of noise values will be beyond that range. So we don't know what the instantaneous value of the noise is, but we have a pretty good idea of the range of amplitudes that we should experience, and we know what their general distribution is going to be. So that allows us to not be able to predict the instantaneous value, but have a relatively good understanding of what our design constraints will be, because we should expect our noise to not exceed particularly boundaries except in extreme cases. All right. Our standard deviation for our noise in this case is what's going to be called the RMS noise voltage. And this is simply going to be the square of our noise voltage quantity. Okay. You guys probably already know this, but because I talk about this way back in my Circuits 1 class and it will eat up roughly 45 seconds of time, I will talk about why it's called the RMS value. It is the RMS value because it is the root mean square of our signal, right? So we are squaring our signal. We are taking the arithmetic mean or the average, and then we are taking the square root to get our RMS value. All right, so moving along. Noise sources can be correlated or uncorrelated, okay? So let's talk about what the difference between those two things are by using a simple example. Where are you from? What actually, let me ask you, you're a critic, right? Where are you from? India. So what's the biggest sport in India? Is it, shit, now I'm drawing a total blank. What's that thing that came from Britain? Cricket, there we go. Is it cricket or is it what us dumb Americans call soccer? It's cricket. Okay. I don't know anything about cricket except for what I saw in a very short documentary. I do not understand it at all. I know that there are like 5 different versions of the game or something like this. Like there's those really, really long versions that they still play in Great Britain that take multiple days. My understanding is that there's a different rule set now that's largely been popularized in, I want to say, India and Pakistan and stuff like that, where the games can be accomplished in a much shorter duration of time. Is that fairly accurate? Yeah. Don't remember what it's called. Don't know what any of the team names are or anything like that. But a cricket game or a cricket match or a football game or something like that would be a great place to witness both uncorrelated and correlated noise, okay? So if we're at a cricket match, everybody is talking to each other and having a good time while they pay attention to the game and all of that kind of good stuff, right? All of those individual conversations that are going on are examples of uncorrelated noise because they don't have any real relationship to each other. So some people in this part of the stadium are talking to each other, other people in the other part of the stadium are talking to each other, but there is no linkage between those two noise sources. So that's uncorrelated noise. Now, what happens if I'm going to assume scoring happens in cricket. I don't particularly understand how or why, but let's say that a good play has occurred. What's going to happen? A consensus of most of the people in the stadium will react at the same time to that impulse, right? That is an example of correlated noise. So those are the differences, okay? Now, if noise sources produce uncorrelated noise voltages VRMS1 and VRMS2, the total noise voltage VRMS, let me put a comma here, total will be equal to the square of VRMS1 plus the square of VRMS2. And then we take the whole thing. So effectively, we add the powers together and take the square root. Right? If there were a resistor thrown in there, it would be the powers or whatever. So we're taking the Vn squared quantity, because Vn squared should be the exact same thing as VRMS squared, since VRMS is Vn, the square root of Vn squared, right? So we're adding those noise voltage quantities and then taking the square root of the sum. If instead our noise sources produce correlated noise voltages, VRMS1 and VRMS2, the total noise voltage will be given by VRMS total is equal to VRMS1 plus VRMS2.